Okay, so good afternoon. So I'd like to get started now. I just have two sort of quick administrative announcements before we start talking or go back to talking about how you interpret or do empirical work. The first announcement is just a reminder that the problem set is due on Friday, so just bring it in and give it to me or give it to Gavin. He should show up at some point during class to pick it up. The second announcement is related to an email that I sent out through DSpace like a couple weeks ago, I think, about the DSP program is looking for a note taker in this class, and they emailed me like a few days ago and said that nobody has responded. So they want me to make an announcement in class. And just to be clear, so basically they would be paying you to just, if you're already taking notes, they would essentially be paying you to just share those notes. There's not really, if you're not taking notes right now, you don't want to. Okay.
Yeah, I think that's like the problem. I mean, I saw that.
Right.
I don't really
You don't see, like, okay, so I mean, I guess, well, I'll liaise with them some more. It's also the case we have a podcast. But the whole thing is that basically I'm liaising with them, and they're like acting on behalf of somebody else, so there's not like really a sort of direct connection between demand and supply here. Okay. So today I just want to continue talking about conditional expectation functions, which is where we left off on Monday, and then we'll start talking about linear regression, which is basically sort of like the bread and butter of econometrics, which is like empirical estimation in economics. So last time we ended up talking about how you could calculate this thing that we call the conditional expectation of y given x, and it's just what it's trying to represent, or what's trying to capture is just the average value of y, or how the average value of y evolves as x changes. So like in this particular graph, you can see this red line, which is just taking the mean of hospitalizations, the variable on the y-axis. It's basically calculating a mean at various points of air pollution, which is the x-axis. You can see that that thing is kind of trending upwards, which is telling you that there's more or less a positive relationship on average between changes in air pollution and changes in hospitalization. So the reason that we are interested in conditional expectation functions, the reason they're useful is because they describe how y changes on average as you get changes in x. So unlike the covariance between x and y, so if the covariance is positive, we know there's a positive relationship on average between changes in x and changes in y. If it's negative, then we know that those things are negatively correlated. But it's not so useful for sort of forecasting the magnitudes of changes. The conditional expectation function, on the other hand, tells us exactly how much we should expect y to change when x changes by 1 unit on average. So when I say exactly, I mean that it's giving us like a number, so that if x increases by 1 unit, then we might think that on average y would increase by 0.47 units or something. But again, this is all in terms of expected values. That's not to say that in any specific situation, if you were to increase x by 1 unit, you would expect to see an exact response of the y variable of 0.47 units or whatever the number is that you're expecting. So the amount of the change, the magnitude of the relationship can actually vary over the range of x if the conditional expectation function is nonlinear. So like the one that I showed you just on the last graph basically looks nonlinear in the sense it's not just a straight line, it was more sort of like a U-ish shape. And so what that's telling you is that the first derivative of that function, which is telling you how much y changes on average with a 1 unit change in x, that first derivative is not constant. It's not a linear function. The first derivative is going to vary depending where you are in that x range. In terms of notation, you'll, like if I'm referring to the conditional expectation function, sometimes you might hear me refer to it as the CEF, which is just the acronym for it. So we have a technique that we call linear regression. And it's basically a method that we use to try to estimate or at least approximate this conditional expectation function that we'd like to know. So in theory, we could estimate the CEF, the conditional expectation function, as I described in that previous example. So we could go through all of the different points in the support of air pollution, which runs from like 1 unit to 6 units here. So when I say the support of a variable, I'm basically talking about the range over which you observe the values of that variable. So we could go through the support and we could basically calculate the mean value of hospitalizations in small areas right around each of the different points of that support. And if we did that, then we'd end up with something like the red line. But there are several drawbacks to doing things that way. One is that the procedure is somewhat complicated. So what I just described to you is actually this sort of fancy non-parametric regression procedure that's called kernel regression. But it's kind of complicated, and computationally, if you have a large data set, it can take a while to do that. Maybe more importantly, the estimate can get unstable for values of x in which there are very few observations. So what you need like really dense data at all of the different points at which you're trying to estimate the conditional expectation function. And if you don't have a really large data set, then you may not have really dense data across the entire support of x, or in this case, the support of air pollution. So I've highlighted sort of an area where that becomes problematic in this example. So if you look at sort of days on which air pollution is between 5 and 6 units, there's really just a single day there. And so the relationship that we're trying to estimate here, the CEF, which we're representing with the red line, is basically being totally dominated by that single data point, right? There are no other data points in that area, and so this one data point is like really pulling up the line right there. And so if you were to look at, like, if you didn't know, if I hadn't plotted the underlying data for you, right, and all I plotted was that red line, then looking at that, you might think like, whoa, from what I can see here, it seems like there isn't that strong a relationship between air pollution and hospitalizations until you hit this like threshold level of 5 units of air pollution. And then between 5 to 6, the derivative is huge. Like the slope of that line is really steep. And so you conclude, well, basically if we're trying to avoid negative health outcomes, trying to reduce hospitalizations, then maybe it's important to keep air pollution below 5 units. But once you get below 5 units, it doesn't matter so much, right? So if you just saw that red line, the estimate of the CEF, then you might conclude that it would be pretty reasonable to do so. But once I show you all of the underlying data, your conclusion would probably change somewhat, right? You'd be like, well, actually it turns out this like really steep slope here is driven by that single data point. And if I were to say draw a line through all of this data, that data point would also lie right on that line. And so you might be more inclined to think that maybe there's just sort of like a general linear relationship that's upward sloping all the way between 1 and 6, rather than that it's pretty much flat from like say 2 to 5 and then goes up really steeply at 6. And the reason that the red line is kind of deceptive in this case is basically that there aren't enough data points up here, and so there's just one day on which it was a high pollution day, and there happened to be a whole bunch of hospitalizations, and that's like sort of pulling the line up because there's really nothing else out there to counteract it. So if you don't have enough data, then doing this type of procedure can lead to erroneous conclusions. So an alternative way to estimate the conditional expectation function would be to assume that the conditional expectation function itself is a linear function of x. So remember again that we're writing this thing that we say is the expectation of y given x is equal to some value, which we'll call little x. But we can just write that alternatively if we wanted to as just some general function h of x. And we don't know the functional form here of h of x, but in some cases we might think that it's linear. So if that were true, then it would have the form that would look something like beta naught plus beta 1 x. So beta naught and beta 1 are like fixed parameters. And so we're just saying that this conditional expectation function y given x is just a linear function of x. So if we're willing to do that, or willing to assume that, then it turns out that we can estimate the conditional expectation function of x using a procedure that we call linear regression. So what linear regression does in a nutshell is that it generates the straight line that best fits the data out of all of the possible straight lines that you could potentially draw, right? So you can think of drawing lots and lots of different lines through this scatter plot that I have up there. You could think of drawing a line that was just, say, a flat line at 15 hospitalizations that went all the way across the top of the graph, or you could draw a flat line that was like at 0 that just went across the bottom of the graph, or you could draw a line that was sort of like the one that's up there, but maybe had a different slope or something like that. And all of those lines are going to fit the data better or worse depending on where they are and how you draw them. But we're restricting ourselves to always drawing straight lines because we're assuming a linear relationship. And it turns out that the line that's actually up there, this red line, is the best fitting of all of the possible lines that you could draw. And when we say that it's the best fitting, we mean that it minimizes the sum of squared deviations between predicted hospitalizations, which are represented by the line itself, and the actual hospitalizations that you observe in the data, which are represented by the dots. So just to make sure that we're all on the same page here. So we have a scatter plot of data. This is y, which is hospitalizations. This is x, which is air pollution. So we have a whole bunch of different days on which we're observing both of these values, and we can plot them against each other. And then we're trying to fit the line. We're trying to draw the straight line that best fits the data. So I'm just going to guess here and say that maybe it's this line. And when we're saying that this is the line that best fits the data, we need some sort of criterion for what's good and what's bad, right? Like it's meaningless to say that something's the best if you don't know, if you can't rank it against other lines or other things. In this case, other lines you could draw, right? And so the criteria that we're going to use is what we call the sum of squared deviations. So for any given data point here, so that each dot is a data point, and what we're trying to do ideally is fit a line that goes through all of the dots. Now, obviously, if it's just a straight line, you're never going to fit all the dots unless you either only have 2 points or so for some reason you got really lucky and all the dots exactly align in a straight line. So in general, you're not going to get a perfect fit, but some fits are better than others, right? So, for example, this data point right there is actually pretty well predicted by the line, right? Like the line almost goes through that data point, but it just misses it. So the deviation between this data point, the daily number of hospitalizations on this day, and the predicted number of hospitalizations, which are given by the line, is only this small amount right here. So that's like the prediction did pretty well in that case. But in some other cases, it didn't do as well. So like over here, you can see that the difference between the predicted number of hospitalizations, which is given by the line, and the actual number of hospitalizations observed on that day, given the air pollution levels were right here, is pretty large. So we kind of over-predicted that day. And then over here, there's another large deviation. So we predicted, given that x was, say, equal to 1 here, we predicted that y would be this value. But in fact, on that day, we observed y that was maybe twice as large. So again, there's a large deviation there. So you might think, well, okay, so if I want to sort of get a measure of the goodness of fit of the line, then I could just sum up all of these deviations. And you'd be almost right. The one thing is that in some cases you have positive deviations, and in other cases you have negative deviations. And so if you sum up all of the deviations, they could end up offsetting each other, and you could end up with like sort of concluding that on average there was 0 deviation, which would be true. But that's not the same thing as saying that you managed to predict all of the things exactly right. It's like that like old joke about the statisticians who go hunting or something, and they see a deer, and one of them shoots like 10 feet to the right of the deer, and another shoots 10 feet to the left of the deer, and they say, well, we got him because on average the 2 shots were right at the deer. It's true that on average they were right at the deer, but that doesn't mean they actually hit them. So we don't want to just add up all of these deviations because you would get sort of some offset between the positive and the negative deviations. So instead we need to do something to make sure all of the deviations are positive unless it's a 0 deviation, in which case you actually predicted it spot on. So what we do in practice is we take these deviations and we square them. So basically your measure of how well the line is doing is you like tabulate all of these deviations. For each deviation you square it, and then you sum up all of those squared deviations, and obviously since you're squaring it, you'll never have a negative number there. You could think of like other ways to do it though. So this is sort of there's like a long historical tradition behind linear regression that goes back hundreds of years. And so because of that we're kind of like I don't know, I won't say culturally, but it's just sort of widely accepted that summing up the square deviations is the right measure of fit. And there are some theoretical arguments for that, but you could certainly imagine an alternative of, you could say, take the absolute value of each of these deviations and sum up the absolute value instead of summing up the squares, right? And so in that case, you again would basically avoid this problem of offsetting positive and negative numbers. In practice, what would happen is that if you're summing up the squares of the deviations, then what you're saying is you really want to penalize cases in which there was a big outlier because you're going to take the difference between that outlier and the predicted value, and then you're going to square it to make the difference even larger. Whereas if you just summed up the absolute deviations as opposed to summing up the square of the deviations, you wouldn't be penalizing the outliers as much. Whether or not like one is superior to the other, I think it's not so clear that. So what we do is we sum up the square deviations, but it's not clear that that's necessarily better than summing up, say, the absolute values. The honest part of it is that if you sum up the square deviations, you can come up with a very tidy formula for what this line should be, and we'll discuss that in just a moment. Whereas if you sum up the absolute value of the deviations and then try to figure out what line best minimizes that sum of absolute value deviations, basically you can't analytically solve for. So you can't like do calculus and figure out what the formula would be. You actually have to have a computer go through and like numerically try millions of different lines and figure out which line minimizes the sum of the absolute deviations. And now these days that's not such a big deal, but 100 years ago we didn't have computers, so it would have basically been infeasible to actually figure out what line would minimize the sum of absolute deviations. Okay, so this procedure that I just described is what we call ordinary least squares. So you'll hear it abbreviated as OLS. And the reason we call that is because that's exactly what it's doing, right? It's basically squaring these deviations, and it's trying to come up with a line that results in the lowest sum of squared deviations. So it turns out that algebraically, if you follow this procedure of trying to minimize the sum of squared deviations or trying to find the line that minimizes the sum of squared deviations, in that case, the linear regression slope coefficient is always going to be equal to the covariance of x and y divided by the variance of x. So again, let's assume that the conditional expectation function takes on this linear form of say alpha plus beta xi, or if you want to do say beta 0 plus beta 1 xi. So this is the intercept coefficient, and then this is going to be the slope of the line. So if we define the conditional expectation function that way and assume that it has this linear form, then we can write yi as being equal to the conditional expectation function plus some leftover. So what we're saying is that the expectation of yi given xi is equal to some value, which we'll call little xi, is equal to, just to get the notation consistent here, I'll say alpha plus beta xi. So we're saying on average, if x is equal to little xi, then y is going to be equal to alpha plus beta xi. But of course, in any given sample, for any given observation, it doesn't have to be exactly equal to that. So there's going to be some sort of deviation or some sort of residual that gives the difference between what our predicted value of xi would be, or our predicted value of y would be, and the actual value of y. So we're going to call that deviation or that residual ei, and then yi is equal to its predicted value plus the deviation, ei, which alternatively we could write as alpha plus beta xi plus ei. So once we've written down the problem this way, we can actually write down an objective function and try to solve the problem. So this is, like we talked a few lectures ago about solving for efficient allocations and trying to figure out like what a firm would do if we're maximizing profits. And this is kind of the same thing, except now we're not talking about the behavior of agents like firms and individuals and social planners. Rather, we're talking about how we as researchers might try to fit a line to data. But at the end of the day, the calculus is going to be the same. So we have some objective function that we're trying to maximize or minimize. In this case, we're trying to minimize it. And so the objective function is that we want to minimize the sum of squared deviations between our predicted values of y and our absolute value, or our actual values of y. So we can write the deviation between the predicted and the actual value of y as being the observed yi minus our expectation of y, given that x was equal to little xi. And that's, of course, alternatively equal to yi minus alpha minus beta xi, given that we said that this conditional expectation function takes a linear form, alpha plus beta xi. So for any individual data point or any individual observation, that's going to be the deviation. And then we want to basically maximize the goodness of fit, like how well we fit the data, which is the same as minimizing the sum of squared residuals. So that's going to be equivalent to solving what's up on the slides there, which is to minimize the sum from I equals 1 to n. So we'll assume we have n observations in the data set, but you're minimizing the sum of the residual terms or the deviations, which are ei squared. And that's, of course, equivalent to minimizing the sum of yi minus the conditional expectation of y given x. And we can also substitute in alpha plus beta x there for the conditional expectation function. So it turns out that if you solve this problem, then what you'll find is that beta is equal to the following thing. So it's equal to the sum over I, or sum over I from 1 to n, of xi minus x bar times yi minus y bar divided by the sum from I equals 1 to n of xi minus x bar squared. And we can actually rewrite this formula. So if you remember from statistics, when you want to, so if you want to calculate the sample mean, that's just the sum of xi from I equals 1 to n divided by n. So x bar is just 1 over n times the sum of the xi's for the entire data set. So that's that's what we call the first moment of the data. And that's your estimate of the mean. If you then want to estimate the variance, then the variance is just the sum, or your estimate of the variance is the sum from I equals 1 to n of xi minus x bar squared. So remember, the variance of a variable is basically measuring like the dispersion in that variable. It's the dispersion around its mean. So you're taking the difference between the actual, for each observation of x, you're taking the difference between the actual value, the sample mean, take that difference, square it up for the same reason that we were squaring the squared deviations on the graph, sum that up, and then divide by 1 over n to reflect the fact that you don't want the variance to explode just because the data set is getting larger. So that's equal to the variance. And then, so I hope you basically remember that formula. The last one that you hopefully remember but may not is that if you then wanted to calculate the covariance between two variables, that would be, so similarly, that's going to be the sum from I equals 1 to n of xi minus x bar times yi minus y bar, and again, rescaling that by 1 over n in the front. So if you take the expression for the variance and you take the expression for the covariance of x and y, you can see that on the top, we have the covariance of x and y multiplied by n. On the bottom, we have the variance of x multiplied by n. So the n's on the top and the bottom would cancel out. And so beta is then just going to be equal to the covariance of x and y divided by the variance of x. So in any given sample of data, if you had observations on x and observations on y, and you wanted to calculate the regression coefficient, you could actually do that without even running a regression per se. You could take this formula and you could just tell Stata or whatever statistical package you happen to use to report to you the sample covariance between the two variables, the sample variance of x, and then just divide those two things by each other, and you would get the OLS coefficient. So I didn't bring your group identifiers today, but that shouldn't really matter. So I just want you to do a short exercise where, where's this? So I just want you to do a short exercise where you solve for alpha. So I gave you the solution for beta here, and if you wanted to, you could actually so you could solve, you could come up with this on your own rather than having me give it to you. So you have this objective function here where you're summing up all the square deviations. It's a function of the data x